Hi, my name is Kaushik Veeraraghavan. I'm a software engineer at Meta. Today, I'm super excited to be presenting to all of you about how AI is reshaping our industry. Now, we at Meta find ourselves at the center of this AI revolution as we built and developed PyTorch over the past 5 years, which is now part of the Linux Foundation. PyTorch is now the leading framework for AI researchers and industry practitioners to solve the most complex problems affecting our industry. For instance, PyTorch has been used by the OPT3 language model, and it's also used by DALI for the automated image generation work that it's doing. In this talk today, I'm going to share how Meta is expanding beyond PyTorch and is continuing to focus heavily on building an awesome ML development experience by supporting AI holistically across our entire infrastructure stack. I'd like to start this journey by first talking about where we are as an industry overall and as a community. First, we're finding that AI is affecting every company out there and every possible workload. And as a result, we're projecting an exponential increase in the amount of capacity for AI with no clear end in sight. And it isn't just capacity alone. We're also finding that AI workloads have a voracious appetite for data. Perhaps some of you might have heard from my colleague Aparna Ramani at Meta at the recent Data at Scale conference, where she was sharing that a few years ago, the most difficult and challenging workload that was running on top of the data warehouse were our analytics systems. But now we're finding that ML has caught up and far surpassed the needs of these analytics systems. Aparna also identified how this growing need of data by AI is causing us to redesign our data warehouse, both to improve the volume and the freshness of data delivered. So if you get a chance, catch that talk. Third, we're finding a significant evolution at the software layer. Specifically, while we've invested and built out PyTorch over the past few years, we're finding that increasingly, as AI is adopted by more and more industries and more workloads, we're finding that the needs of PyTorch itself and the surrounding ecosystem are growing. So we're now needing to support the end-to-end needs of ML development. And this goes beyond PyTorch, which is just the authoring system, onto areas like data management, feature engineering, modeling, scheduling, and lifecycle management overall. So to quickly recap, we as an industry are finding this massive increase in the use of AI for all our workloads. And this is leading to a massive growth in terms of capacity needs, shifting data demands, and a significant evolution of the entire end-to-end ML development system. Now, this is a lot of change, and it's all happening concurrently. So some of you might be wondering, why are we investing so much in AI? So let's quickly dive into this. Now, there are many amazing applications of AI, and what I'm going to do here is just choose to highlight one of the ones that appeals to me the most, which is the no language left behind, as it's all about growing human connection. Specifically, we at Meta just open sourced a set of AI models that can translate across 200 different languages. Many of these languages were not supported by our current translation systems, so this is a first-time experience for people who practice them. Now, this model has over 50 billion parameters and it was trained using Meta's research supercluster. We find that AI enables a whole bunch of meaningful experiences. For instance, we leverage AI to develop ranking and personalization models for Reels, newsfeed, etc. And we're finding that over a period of time, these models have grown to be multiple terabytes in size, and together they come in to deliver a really meaningful experience. Now that I've recapped a little bit about what we're doing at Meta, I want to take a moment to quickly introduce myself. I'm a software engineer who joined Facebook as its first postdoc intern in September 2011. Now, I happened to join by happenstance. We just had a kid and I missed the academic interview cycle. But as soon as I started here at Facebook, I realized that I was in this amazing place where we were scaling a whole bunch of our systems. And all the software and systems work that I would do was directly affecting the lives of millions and then soon billions of people. So over the years, I've grown a bunch with the company, and my family has grown too. And as you can see in the art behind me, which is drawn by my kids. So as we've grown, we've all changed. And now I find that I've moved beyond my distributed systems background to really start focusing a whole bunch on AI. And when I think about why, I find that it's because I'm passionate about improving the ML engineering experience by really focusing away on the complexities of infrastructure. What do I mean by this? Well, in the rest of the talk, I'm going to give you a guided tour of infrastructure and show you how we need to work well across the entire stack in the service of AI. So, again, what is my goal today? My goal is to make sure that you understand all the pieces that need to come together in order to be able to scale AI and meet these amazing and challenging needs that are developing in our industry overall. And in order to start off by describing the set of components, I want to start at the very base of infra. I'm going to use Meta's infrastructure as a reference throughout this deck. And here I depict for you our current data center footprint. From its humble beginnings with a single data center building in 2010, we've now grown our data center fleet so that we operate many tens of data center buildings across 21 geographical regions. While most of these regions are in the US, we also have a presence in our EMEA region, as well as in Asia. And it turns out that having this global deployment of data center regions is really interesting and requires us to address all sorts of new questions. For instance, how would we connect these data center regions to each other? In this video, you can see these yellow lines, which are the subsea optical cables that we need to lay across the Pacific and the Atlantic Oceans to connect our European, Asian, and US regions to each other. Further, you might notice these little squiggly blue and red lines in Europe or in the US. Those are our terrestrial networks that are also connecting these regions. So we start off by describing the ML developer experience. We started describing a little bit about PyTorch and the applications that are written. Some of you might be wondering, how is this ML experience connected to what I just described, like data centers and network? How do they fit in? So I'm going to use this iceberg as an analogy in the rest of this talk. Like an iceberg, at the surface, you find that there might be a whole bunch of interesting work like AI algorithms, math, as well as software systems that are required to translate these ML engineers' ideas into real programs, which can solve our problems. But then as you look under the hood, you realize that it's far more complex, and we need every layer of the infrastructure stack to work together to support AI. So let's start off at the very top of the stack. This is roughly what the ML development experience looks like. So for starters, we might have ML engineers who want to solve a problem. They might start off by using PyTorch or one of these open source frameworks that are similar. And then really what they need to start doing is understanding what are the data sets that they want to leverage and what features in those data sets do they want to take advantage of to develop their AI models. After spending a bunch of time working through that layer, they then run a training loop, which runs on one or more computers. Eventually, this training loop, which might run multiple times over the sets of machines, finally converges, at which point we can publish a model and then use the published model to serve our end user traffic. Note that our work isn't done here, as we learn from the user experience and continually refresh the model itself. So how are these models developed? Remember that I shared how we find that PyTorch is the largest ML framework right now? In addition to PyTorch, TensorFlow, ONNX, and there are several other systems that are often used by ML engineers to think about the problems that they're solving, quickly experiment, and then deploy their trained models to production. A key lesson that we've learned over the past several years is that PyTorch's eager mode is preferred by ML engineers as it enables quick iteration and debugging during development. So what we've tried to do is take that understanding and push it through our stack. How so? Well, first, recall the iceberg. What I just shared is at the very top, right? We use PyTorch and the related ecosystem as the front-end experience of authoring and deploying a model. Next, let's look at the hardware system where the code actually runs. Specifically, we could have the hardware, and it could just be a CPU on a regular x86 machine that's running it. But more recently, what we're finding is that while ML programs can run on CPUs, we find that specialized accelerators, such as ASICs or GPUs, are preferred as they can dramatically speed up the ML computation. So at Meta, in addition to GPUs, we're also driving the development of domain-specific accelerators with PyTorch Eager Mode. And this allows us to co-design the chip architecture, the compiler, and the interconnect, as well as the overall system to make sure that we can serve our ML engineers' needs well. And we find that this approach is often in contrast with that of other chip vendors who might prefer just TensorFlow or ONNX, which just supports static graphs, while our approach with supporting ego mode allows us to meet the engineer's needs in a much more holistic way. Now, as the ML models themselves grow in size, we find that a single accelerator or GPU is not enough. So here we've depicted a GPU server, which has got 8 different GPUs connected to each other, as well as their interconnect. Now, it turns out that, for the really large models that I described for you, that we use for ranking, recommendation, content understanding, etc., even 8 GPUs in a single server aren't enough. We often need to connect many of these servers together. So now you might be wondering, how are these servers interconnected? Traditionally, we might have a single network that connects these machines, but for our ML workloads, we find that we need 2 different types of networks. First, we have a front-end network that connects all of these machines to the training operation itself, where a user or a request from an ML engineer might kick off a job. And secondly, we also need to invest in a very high bandwidth backend interconnect. So the front-end network is a single network cable or a link that connects to our different machines. But the backend network is actually a really high bandwidth network that connects all the GPUs on these machines to each other. So what we've just described is how our ML engineer can write a program. It can run on custom ML accelerators, which are interconnected via 2 custom networks, a front-end network and a backend network. Next, let's delve into what else is needed, starting with the storage layer. Specifically, we need to make sure that all these ML programs that we want to run are fed with data. The data can be a set of images which are used by content understanding workloads to detect humans from, let's say, cats or dogs, or they can also be from our ranking and recommendation systems, which need to pull in a whole bunch of data to run the training jobs. Now, the training job itself might run for many days or even weeks, right? Not just seconds, like the online serving stack. And this requires that sometimes we have the entire system be resilient to failures. For instance, we might see individual machines die or individual network units just get disconnected. So in order to support this well, we've also built a system for checkpointing state across all of these machines that are collaborating together in order to run the ML program. This checkpoint and any associated state also needs to be stored in our storage system. So what this slide now depicts for you is the entire training cluster. It's a collection of GPUs distributed across many machines, as well as the storage components, ingestion systems, as well as checkpoints that need to all come together in order to run this training jobs. Some of you might be wondering, why do we invest so much in this complex hardware or on this stack? Well, I want to give you a quick example. In Meta's recent earnings call, you might have heard that we launched a new AI model for Reels atop our GPU infrastructure. And we found that this directly led to a 15% increase in watch time. So what we are finding is that investing in these new hardware concepts and then supporting them well with our storage systems as well as our network systems is allowing us to make a meaningful difference in the business. This brings me to the first principle that I want you all to think about, which is when you think about these AI programs, it's important not just to focus on the framework and the hardware that it runs on, such as GPUs, but really consider the entire holistic stack, right? Which includes storage and the data ingestion systems and everything else that's required for the training loop. So, all right, I just spent a few minutes speaking with you about the ML programs and then the storage and the network interconnect. Let's now delve deeper into what is it that supports this entire stack. Basically, I can't just get all this hardware and power it up, right? I need to start thinking a little bit more about what type of jobs are running here. So specifically, we find that while this is a simple training cluster, and this is just a simplified view, in reality, we need to connect a whole bunch more GPUs to each other. And we need a whole bunch more machines for this. So in this figure, we are now showing you something that's a little bit more realistic, where we have 512 GPUs connected across 32 racks. We call this an AI zone, which is because we've outfit the front end and the back end networks appropriately to support all this AI hardware. Now, looking at the GPUs themselves, we find that today the average GPU consumes about 300 or 400 watts of power. But in the future, we expect that the power needs of these GPUs are going to hit 800 watts or more, at which point we can no longer just rely on air to cool the GPUs themselves. And we now need to turn to new technologies. So we are investing in a completely new rack design that allows us to support liquid cooling. This is really, really challenging because in addition to just having the servers and these GPUs and all the connecting cables and dealing with the physical repairs on them, we also need to deal with the complexity of piping in hot or cold water into these racks and then making sure that we can operate all of this complex infrastructure well in case of leaks or in case of blockages in the system. Further, we've also realized that we need to think deeply about how to partition our data center space. For instance, we might have a bunch of high-powered GPU racks, which require liquid cooling support, but we also have a bunch of compute and storage machines, which don't require all this fancy liquid cooling. How do we partition the space and proportion them? After a bunch of work on this, and obviously a bunch of errors and mistakes, we've kind of learned that we need to optimize the system for each workload. For instance, we find that content understanding, which generally operates on speech or text or videos and images, needs less data on average than our ranking and recommendation systems. So we think very deeply about the workloads that we're deploying and the support that they need in terms of hardware, in terms of the racks, the ratio of GPUs to storage to compute, and then the networking needs themselves in order to fit out this space. This is a really neat optimization problem that we're continuously investing in. So at this point, you can figure out where I'm headed. We started off with hardware, then we went to network, then we went a little bit into rack design and cooling. Let's just delve all the way into data centers. Some of you might just think that the data centers are just large warehouses. Why would they need to know anything about AI? So let's dig into this. We're finding that just as we co-design the hardware, network, and software, if we extend this all the way to our data center design, we can perform dramatically better. Specifically, remember how I'd shared that we have a global deployment of DCs, data center regions, many of them in the US and then the rest of them worldwide? Well, we need to think really deeply about how much backbone capacity we need across them for our subsea network. We also need to think deeply about which regions do we want to run these AI workloads in, and then how do we design these AI zones and the ratio of the different types of storage, compute, and GPU hardware that we allocate in them so we can appropriately build the backend and the front end networks. And then we need to think deeply about how much of this network and AI zone capacity do we want to provision with servers to give to different workloads. All of this system needs to work together, which brings me to my second point, or second principle rather, which is that if you're able to co-design the entire end-to-end system, then please do so. Don't just focus on the ML programs and then maybe the hardware and the software systems that support it, but instead go deeper. Think about the racks, think about the network, think about the cooling, and then think about the entire data center space as needed, as you can then build a much more comprehensive solution to scale AI. Now that we've described all the supporting physical infrastructure in detail, let's delve into the ML developer experience itself. I'm going to now share for you a slide which looks a little bit busy. Please pardon all the different boxes and arrows here. I want you to just pay attention to the top line, which are all the major circles at the very top. This is the ML experience that we described before, where we have an ML engineer defining a task, thinking about what data sets they want, what type of transformations they want to perform on this data, do all the feature engineering work, and then kick off the training loop. The training loop is shown in pink here. Finally, when the training loop is done and converges, we get a model that can be published and then served using our inference systems. I'm going to focus a little bit on this pink circle here because I'm just going to highlight one of many challenges that we've had to solve and one that we're pretty proud of in making the entire ML development experience seamless. Specifically, I want to call out that this training component is also super critical because this is how the programs that the ML engineer write runs on the rest of the physical infrastructure, namely all these servers in an AI zone across these data centers. Now, think back to the early part of the talk when I showed you that we have a global deployment of data center regions. What we're finding is that when we operate really large-scale infrastructure of this type, we might see individual failures for, let's say, individual network devices or maybe individual servers. That happens all the time, and checkpoints work well for that. But what happens if there's a massive power outage that affects parts of California or parts of the US? Or maybe there's a network cut in the submarine cable that connects our European region to our US regions. In this case, that would be catastrophic failure in terms of like data or the processing of these ML jobs. And our ML engineers might need to learn about underlying components of infra. Well, in our effort to abstract things away, we've actually come up with fantastic fault tolerant systems. Here's what we do. We have intentionally taken all the data that these ML programs consume, replicated them across our US regions and across a subset of our European regions, such that if we see a large scale failure, we can seamlessly transition the ML job with its existing checkpoints from one region to another and continue training the job without any engagement or interaction from the ML engineer. While this might seem simple, it actually requires all the underlying layers of the stack. For instance, we need to make sure we have adequate data center capacity, network bandwidth, we have the right number of racks, and we have the checkpoint and the storage systems ready in order to migrate these jobs over. So what does that bring me to, right? That brings me to my final principle, which is that I'd encourage all of you to plan for innovation as AI is evolving dramatically and continually, which will require you to revisit all of your assumptions in your infrastructure stack, just as we had to deal with for our fault tolerant systems and our checkpointing systems, and the data centers and the network and everything else that we've described. And now I hope you also understand the complete picture, which is while the ML engineer generally just builds ML programs and tries to run it on hardware that's optimized for that workload, if we are able to get the rest of the infrastructure stack to recognize the needs of the workloads that are running on it, we can dramatically optimize the system and unlock massive value. As I close out this talk, I'm super excited. I want us to all think about how we can build for the future because AI presents us with amazing opportunities. I leave you with three principles. First, I'd encourage you to think beyond just the ML programs or even the GPUs that they run on to the software stack and to the storage systems and the data ingestion systems that are required to feed these ML programs. Next, if you have the opportunity to, I encourage you to co-design the end-to-end system beyond hardware, going to the network, the rack design, the data center space, and everything else in between. And finally, I want all of us to be cognizant of the fact that AI is evolving dramatically and continually. So if we plan for the future and we can take adequate steps, sometimes years in advance, to support the needs of AI, we might be able to make dramatically more progress in this space. I'm excited to see what all of us in this at-scale community achieve in the coming years. Thank you so much for your time and attention.